Okay, YouTube, in this video we're going to be discussing exponential growth models, or modeling situations that grow exponentially using this exponential growth model. So I say when a real life quantity increases by a fixed percent each year, we know this percent, this fixed percent, or other time period, that is, for instance, a year could be one of them. But the amount y of the quantity after t years can be modeled by this equation here. And one thing that I kind of want to point out is we've been talking about exponential growth models. So I'm just going to make a quick relation here and say that when we're looking at these exponential growth models, we're often looking at quantities that have an x and a y, but we say the y value is kind of on the y-axis, but it's a function of time. That is, time is down here flowing from left to right. So instead of an x value right here, we're going to see that we often use a t. But like on a calculator, you could totally put an x there and we say x represents time, generally speaking. And then we say, okay, well here everything is pretty much the same. We have an a value still out front, and then we have some b value here. It's just that our b this time, we're referring to our base, is being equal to this 1 plus r quantity here. And one thing I want to tell you about this 1 plus r is it has a name. We refer to it as the growth factor. Okay, so recall first of all what a factor is. A factor is a number that when you multiply by another factor it gives you a product, so we're multiplying here. And also keep in mind that when you talk about an exponential growth function, y equals a times b to the x, we say whatever x is here, this is really the same thing as a times b times b times b times b times dot 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 times b, and we have x factors of b being multiplied together here. So just whatever the value of b is, that base value, we're going to call that our growth factor. And the thing that makes that the growth factor, by the way, is this. Let's say I have, hypothetically, somebody agrees to give me as repayment method, a penny on one day, but then 2 pennies the next day, and then 4 pennies the next day, and 8 pennies the next day, or they'll just give me $100 up front. I might go with the pennies because in this example we would say that I'm starting off with a penny. So like, here's what I have, and every day what's happening to this penny? Well, what's happening is I'm taking it times 2, but I'm taking it times 2 every day. So like the second day would be 2 times 2 times a penny, and the next day would be 2 times 2 times 2 times a penny on the third day. So we'd say, more generally speaking, we say as the days flow, this is what we're looking at here. And so in this case, my growth factor would be this base value here. And I call this the growth factor because what's happening to my penny every day? It's doubling. So one thing I want to kind of say here is this. When you look at your growth factor as a decimal, one thing we could do is we could reinterpret it as a percentage and move our decimal twice to the right and say that this is 200%. But what you're really saying is we are taking 200% of the amount that I'm starting with every day. 200% is twice as much, which makes reasonable sense here. So let's imagine the hypothetical situation where I take my penny that I'm starting with and I take it times 1, or 1.00 to the x. In other words, I'm finding 100% of what I have every day. And what is 100% of something? Well, it's what you started with. But again, if you multiplied by 1.00, this would never change. So when you look at this up here and we say that it's 1 plus r, I just kind of want to talk about why we put this 1 in here in the first place. But because that 1 represents 100% of what you have, and then this extra little bit right here, this r value, kind of represents how much above or below 100% you're going. So if 1 plus r is our growth factor, then we say r is the growth or decay rate. There is a difference between growth factor and growth rate. Growth factor is this entire thing, 1 plus r. What's our growth factor and decay, and initial amounts on these down here? We're going to say that our initial amount is always the a value up front, and our growth factor is this thing right here. But in this first instance, we would say that the initial amount, initial amount of whatever it is we're starting with, is 42. It's this is we're starting with 42, and it's growing by a factor of 1 plus 0.07. What I'm going to do is I'm going to call this GF, growth factor, and I'm going to say that it's really 1.07. So the thing I'm kind of trying to indicate here is this. How is it growing? It's growing by 107% every time we compound this. In other words, it's 100% of what we have plus another 7% of what we have. Okay, so let's run through all of these really quickly here. We say that initial value out here, this a value, what we start with, it's actually 1. So we say, I'm going to say a equals 1. I'm going to go quicker on these ones here. And we say the growth factor on the second one would be 1 plus 0.7. That's equal to 1.7. I'm going to write 1.70. This is actually 170% of what we're starting with every time. And so this one down here, we're saying our initial amount we're starting off with negative of something, negative 5,000 of something, and our growth factor is 1.26. It's growing by 1.26 every year, or every amount of time. And then down here we say our initial value is negative 2,000. Okay, and we say our growth factor here is equal to 3, or 3.00, or you're tripling something, so it's 300% of what you started with. Okay. So now, knowing what we know about exponential growth models, we say that we could basically model anything so long as we know what we started with there and what the growth factor is. We could say, well, here's what it's doing over time with y and t, or y and x. So let's look at this example here. It says in January 1993 there are about 1,313,000 internet hosts. It says during the next 5 years the number of hosts increased by about 100% per year. So we're going to write down a few things here. We're going to say, first of all, our initial amount is this 1313000 number. So we're starting with this many, and this 100% per year, that's a rate. That is a rate at which it's growing per year more. So when we say write a model giving the number h in millions of hosts t years after 1993, so t represents the number of years after 1993, and then use that to find out how many hosts there'd be in 1996. What we're really saying here is this. We could write this with a y equals initial amount times base to the power of x. We can do this. We were asked to write it as h instead of a y, and that'll still equal initial amount times base to the power of t, where t is time. So in this first case, we'd say our initial amount is this 1313000. 1313000, and in each case we say it's 1 plus r, where our r value is 100%. So now, since 100% is not a decimal, we need to write it as a decimal. So notice that I say this here. We say it must be, the value of r is the percentage of increase, and it must be expressed as a decimal. Okay, we're going to plug in a 1 right here, and we say 1 plus 1. So in other words, our model, I'm going to write this here, this is a model. We haven't done anything with it yet. We say that the number of hosts is equal to starting at 1,313,000 and then saying it's growing by 1 plus 1 to the t. I'm going to say that's 2 to the t. I'm going to say that's 2.00 to the t, just to emphasize the fact that it's growing by 200%. That is, it's doubling every time. So this right here, we want to use a graphing utility to graph this model. So I'm going to hop over to Desmos here. This is going to be a really tall graph. I'm going to say y equals 1313000 times 2 to the power of, and I have to use an x. So here's our function here, and I'll change our grid so that we're going from x represents time. We'll go from negative 1 year, so 1992, out to, and we'll go like, I don't know, like 15 years later. And we'll go by steps of 1. So now, on the y-axis, shoot, we have to go like, I'm going to go negative 100 just to get below the x-axis there. We have to go up to like 1313000, so that's 1 million. I'm going to go up to like, 15 million. And so we can see this here. These are in millions on my y-axis, it seems here, 2 million, 4 million, 6 million. But we can see that over time, we started off in the first year here, we had 2.626 million. That's in 1994. In the very, very initial amount of time, we say 1.313 times 10 to the 6th was what we started off as. So here's our graph, and we can see our hosts growing over time. Okay. So now that I see this here, what I want to do is I want to use this graph to estimate the year when there were 30 million hosts. So the interesting thing is, when I look at this here and I say, okay, well, we've got it in millions on this y-axis here. I'll change it here in a second. Actually, let's just change this right now. I want to go on the y-axis by steps of, let's go by 5. It's going to put it in times 10 to the 6th there for us. But basically, we want to say when were there 30 million hosts. So, I've got to help you guys out here a little bit. We say 30 million hosts would be right here, this 3 times 10 to the 7th. So I'm going to move this down a little bit here, but we say roughly, 30 million hosts would be about, try to get this right on there, right on the money. About right there, okay. And so we'd say we had 30 million hosts in about 4.51 years after we started, okay. So on our graph that we could have drawn by hand, as a matter of fact, we could have said, hey, I know that there's an asymptote here. It goes through this point right here. This is 0.1313000. And I could have said that here's my graph. But basically we're saying when we want to know when is the hosts When are they equal to 30 million? We would say that it happened at about 4.52 was your time. So now what I want to kind of indicate is this very last part. We say this is years after the initial time, which is 1993. So if we said what year was it, then we'd have to say it's 1993 plus 4.52. So it'd be 1997. It's kind of fun to say. This would be the year, we'd be halfway around the sun for that year, okay? But this is what an exponential growth model is, the difference between the rate and the growth factor, and how you can just write a simple model knowing what you started with and what your growth factor is. Cheers.